Okay, in this part we're going to give the theory that explains this effect. We said that if you move a magnet, a permanent magnet, upwards towards a loop of wire, the loop of wire has no source of EMF itself, there's no battery or anything. So the only way a current can be established in the wire is if it's due to this movement of this magnet upwards. And we said that when the magnet moves upwards, experimentally, we show that there's a current in this direction, which means that we predicted that there's some kind of electric field, a new kind of electric field that's in this direction, which makes the negative charges move opposite the electric field. And so the negative charges move like this, which means the current is this way. And that's the observation. So now we want to see the theory that can explain this. And the theory, this is what it looks like. It's called the Faraday Maxwell equation, and it's always valid. So this is one of Maxwell's equations. We're not going to use this Maxwell equation in this form to solve problems. We're going to make some modification to it, a simple modification in a while. But I just want you to see the equation as it is in reality. And it's a bit not that easy, it's a bit difficult, but we'll go through these slides and just try to watch and see. We're not going to use it in this form, so the rest of the slides, just try to watch and see how things work. So let's get started. So first, in a law like this, you have ds, so you need to integrate electric field dotted into elements of length along a closed contour. That's why you have this circle here. And you have here an integration of something dotted into dA. And dA, this integration is done over the area that's enclosed by this contour. So you have a contour on the outside, that's the circle, and you have the ds vectors going around the contour. And then you have an area, this blue area, that's subtending this contour that's enclosed. And we want to integrate over the area something, and so we want to relate this integration over the contour to the integration over this area. So we need to establish a relationship between the ds vectors and the dA vectors for the area, because this is an open surface. So should we make the area vectors this way or that way? We need to make a convention. The convention is made in a way that this law applies and is related to the physical thing that we see experimentally. So if you put your fingers in the direction of ds, you curl your fingers in the direction of ds, the dA vector will point in the direction of the thumb. If you take this relationship between ds and dA, then this equation will be valid the way it's written here. So that's all what we need to know, that the ds and dA are not arbitrary. They have to be related in this particular way. So let's see what the rule is saying. What do we mean first of all by B? It says here partial B by partial T. What do I mean by B? Remember we said this ds vectors, they go around a closed contour. And this contour, this closed contour, then has a certain area enclosed in it. Well, cut up this area into small elements of length, and the same way we always do, define an area vector to be at the center of each element of area. There's an area vector, it's perpendicular to the surface. And we said it's going to be in this direction because of the right-hand rule, it's going to be pointing upwards. So what do we mean by B then? B is the magnetic field at the center of each one of those elements of area. So that's what the B vector at that location is then. Of course, you have to do the same thing for all the other elements of area, but we're going to focus on one of the elements of area only for now. Now, as the magnet goes upwards, what happens to the value, to this B vector? Let's see what happens to it. It gets bigger and bigger, right? Because when the magnet gets closer, the value of the magnetic field at that particular point is getting bigger. The direction of the vector may change slightly, but definitely the magnitude is getting bigger because the magnet is getting closer. So if we look at the magnetic field at a time t, and the magnetic field at a later time t plus delta t, definitely the magnetic field vector at a later time is a longer vector, and it points pretty much in the same direction. Maybe the direction changes a little bit, but it's still pretty much in the same direction. So what does this quantity mean then, partial B by partial T? You're taking a partial derivative with respect to time. Partial derivative with respect to time means you're keeping the the position fixed. We're talking about the magnetic field at this particular point in space only. And we're looking and seeing how does this magnetic field change with time. So this is the magnetic field vector at time t at that point, and this is the magnetic field vector at a later time at that same point. So partial B by partial t means what? It's the magnetic field at the later time, t plus delta t, minus the magnetic field at t divided by delta t in the limit when delta t goes to 0. It's the same definition of a derivative as usual, but it's a partial derivative, so we're only taking derivative with respect to time. We're not changing the position. It's the same position. So if you get b of t plus delta t minus b of t, how do you get a vector minus a vector? We can just take this vector and multiply by minus 1 and then add them. So this is that vector multiplied by minus 1, and then we add them. So when you take this vector and you add it to minus b at time t, this is what you get. You get this resultant vector. So this light blue vector is the one that's b of t plus delta t minus b of t. Okay? Now if you take b of t plus delta t minus b of t and you divide by time, you're not changing anything about the direction then. You're just changing the magnitude. Say this vector. This is the final vector then that represents partial b by partial t. It tells you how the magnetic field at this point is changing with time. And you can see immediately that the dot product between that and the magnetic and the area vector is going to be a positive value. I don't know what it is, but it's a positive value. Okay, now that means this whole quantity, when you multiply a positive value by a minus sign, then the whole right-hand side is negative. It's a negative quantity. And it's going to be the same thing for everywhere on this circle. You can show it's the same. The angle is always going to be less than 90 degrees. So this part is positive. Then when you multiply by a negative value, you get a negative value. Why did we do all this? We showed that integration of E dot ds is a negative value. So if someone tells you that if you go around this closed contour and integration of E dot ds is a negative value, can you conclude from that, is the electric field opposite or in the same direction as the ds vectors? These are the ds vectors. We chose them to be in this direction. So the electric field vector at each location, is it going to be in the same direction as the ds vector or opposite to it? If it was in the same direction as ds, then the dot product will be positive. So obviously the E vector has to be opposite the ds vectors. So that means we've just shown that the E, the non-conservative E that's created, is opposite the ds vectors. Okay, if we have an electric field that's opposite the ds vectors in this direction, what is its effect going to be on negative charges inside the wire? It's going to make the negative charges move opposite the electric field, because the force is Q times E, and Q in this case is negative, so the force is this way. If the force is this way and the charges are moving in this direction, the negative charges, then the direction of current is opposite the direction of motion of the charges, and it's this direction. So we've been able to establish a theory that predicts that an electric field is going to be produced, and it's going to be produced exactly in the same direction to create the current that was observed experimentally. As I mentioned before, this rule, this theoretical rule, we're not going to use it in this particular form. So please take this part to be kind of an inquisitive thing. Read it, go through it, watch it several times just to get the idea. We're going to do this in a much easier way, a simpler way, a bit later.